And this is me, Arman. Very nice to meet you all. And I work as online cloud data access services expert as EUMETSAT. But unfortunately, my colleague Roope Tervo couldn't be able to join us here, but we worked together with him. Also, a team of climate scientists and 2 interns on this project. So I want to also introduce you folks to my team as well. And with that in mind, I want to introduce you also to European public space sector. But let me start by saying that I do not hold any official position to represent any of these institutions. So this will be like the online information available. With this in mind, we have the first in line ESA, which is European Space Agency, and it's the Europe's gateway to space. ESA works together with their national agencies, institutions, and their member states, and they coordinate several missions and programs like Galileo or Copernicus. And we also have in the second line EUMETSAT, which stands for the European Organization for the Exploitation of Meteorological Satellites. And it operates satellites for monitoring weather, climate, and the environment. EUMETSAT also works together with their national agencies, member states, institutions, and the other space-related institutions as well. And we have in our online and archive data lake, we have more than 10 petabytes of data spanning more than 300 collections. I must say I worked at EUMETSAT as a cloud computing engineer between 2019 and 2022, and now as online data access services expert since July 2024. ECMWF stands for the European Center for Medium Range Weather Forecasts, and it provides 24/7 operational service, producing and disseminating numerical weather predictions to its member states and cooperating states. ECMWF also hosts a high-performance computing facility as well as a common cloud infrastructure related with their HPC facilities, and they also have a meteorological archival and retrieval system, MARS, which is providing access to the meteorological data that has been collected or generated at ECMWF over the years. I also want to highlight that I worked at ECMWF as a cloud computing engineer between 2022 and 2024. So let me also give you a quick introduction to climate data records. And it refers to any long-term record of a calibrated data that is useful for climate scientists or climate applications. And the data from current or past satellites or archive are used to generate these CRDs. And these archives basically is the development throughout the satellite program or our satellite application facilities, or SAFs for short, and also can include different collections like Copernicus or other European Union funded projects. This is very nice, but the problem is it is spanning over several petabytes of data, so it's really hard to move the data from one place to another or download the data to your local computer to process. We have multiple data sources and the access methods, so most of the time every new program has its own ways of archiving and accessing the data. The source data can come in various different formats, and some of them are binary formats, so there is some kind of a pre-processing required to start with working with climate data. And to do that, you need multiple libraries to handle all these kind of operations. And we had an idea to make it a little bit simpler for the end user. So we thought if they cannot afford moving the data, let them compute near to data. And this is how European Weather Cloud was born. And the idea is to move the users to close proximity to the compute resources that we have, and let them have some computing resources allocated their tenancy. This is the infrastructure as a service as an idea. But this is not a private cloud, because we are serving cloud resources to our member states and other institutions with the R&D fund, for example. But this is also not a public cloud. So any random citizen cannot go to the web page and sign in and get some resources. Therefore, we are calling it a community cloud for Earth observation and scientists. And the key idea might be to have an ECMWF VM that digesting downsampling and transferring only the necessary data to EUMETSAT VM, which has some kind of a satellite imagery going on. And that is the idea. But the biggest benefit of having European Weather Cloud was that it provides us a well-established way as a meteorological society to work together, coming among EUMETSAT, ECMWF, and our member states. So we have a common platform that we can work together this time. And you might ask why CRDs are important and how we can make it more accessible. So CRDs CDRs are providing long-term calibrated information on how, where and to what extent the Earth's atmosphere, land, cryosphere, like ice sheets, and oceans are changing over long time periods. So this might be, for example, important to analyze the extent of the sea ice of the past decades, and it can give important clues to the climatologist, or this can be an early warning for a fog for aviation. So this and high-quality systematic feature identification is crucial for that reason to further develop the application and ML algorithms to detect these kind of anomalies. And as EUMETSAT, we have mainly two goals to build this Earth system feature detection. One is to support our member states in feature detection from Earth observation data to provide early warnings. This is the fog example that I gave you earlier. And the other goal is to collect a global database for a long time series of identified features. This is the ice sheet example that I gave. Like for 40 years of data, you need to gather this kind of features over a long time period in order to identify the changes. And the goal, like say the end goal, is to establish a community platform to label these features, maintain a database of these features, including the possibilities to explore, visualize, modify, and export all these features that we gathered. To do that, we evaluated models to identify and categorize the tropical storms using pre-trained ML models through transfer learning. I will not go into the details, but if you are interested with them, you can scan the QR code and access to our publication. But TLDR, we were scanning over 2,000 images from Japanese Meteorological Agency, from the satellites from GMA, containing roughly 5,000 tropical storms. You might ask why Japanese satellites? Because Europe doesn't have as many tropical storms as Japanese, so that was like a no-brainer for us to use that instead. And we were like using international best track archive for climate stewardship, IB-Tracks for short, database as the ground truth, because they already identify these things after it happens, and then they are putting it into the database. So it serves as a ground truth. We were manually checking the bounding boxes, but we were not fixing the models based on that. And we were using Dvorak current intensity, DCI for short, to categorize the storms, the different types of storms. And we found out the faster RCNN provide the best performance out of the other three. And in here, you can see actually in the green boxes, you see the tropical storms correctly identified by the model and also present in the IB-Tracks database. And in the yellow one, there are tropical storms detected by the model, but not found in IB-Tracks. But the problem is, the amount of tropical storms are exceptionally many. So as an IT specialist, these are all looking tropical storms to me, at least from my eyes. But the problem with the model is that we need some kind of a domain expert to check all these different labels, because as you can see in the yellow ones, they are not identified as real storms. So this was a false positive. So manual labeling by the domain experts are clearly needed, and you cannot have auto-labeled tropical storms. That's not that simple. Hold on then. Does this mean that the labeling has to be done manually? Like we have, as I said, we had like thousands of images that needs to be identified, and we need climatologists, climate scientists sit on a PC manually labeling all of that. In a completely separate work, I am together with my friends in that project, a completely separate project, we were exploring segment anything model for satellite imagery. Again, I will not go into the details, you can check the publication, but we kind of figured out that SAM is actually doing very well on segmenting the satellite imagery, although that is not trained on that kind of a data set. So we were using Eurostat dataset in this case, but we were not training SAM on the Eurodot dataset. We were just using the pre-trained model. But it still managed to segment the images quite accurately. And here you can see a small application that we developed together with my colleagues at ECMWF at that time. And here you see some kind of a flood in the palm tree area, you see that. And there's a bounding box. And you can make that prediction a little bit more pinpoint with the key points. And when you select the area of interest, you can click the segment, and it will basically segment the image from the rest of the image, and then you can export this information to any tool that you would like to visualize. This can be a QGIS. It's some web map application that climate scientists using. So you can export that annotation and you can use it on your research. So this is something that we were doing at that time, completely outside of this scope. But it gave me an idea. So maybe we can create an environment combining all these different tools, and we will start thinking about what exactly is needed to create such a collaborative environment for the Earth observation scientists. And this is what we came up with. We have ML models, we have Kubernetes, we have climate scientists. We can work together to build an Earth system feature detection platform that can serve climate scientists, a collaboration platform on carrying on their research. So you see there are different tools, and I will be touching them in my future slides. But this is the blueprint for this joint labeling and model development platform, so to say. So on the in the starting side, you have the input label data, for example, IB tracks, and you have the source data. This can be EUMETSAT data store, for example. But the problem is the source data comes in various different binary formats, so you need to do some kind of a data preparation. For example, you can use libraries like SatPy to generate images from that Earth observation data, and then you can put them into an S3 bucket or something like that to store. And then you can parse this IB track labeling as a ground truth, and in here you need some kind of an annotation platform, like we developed it, and I showed you in the previous slide, like something like this. And here we can use a community tool called Label Studio because it has an API and everything, and it can make it easier for Earth observation scientists to import all these things to the platform that they are developing something. And from there, we can actually utilize SAM to help them labeling the features that they detected. And after that, we can export these features to a database. In this case, we are using a PostgreSQL extension called PostGIS, and store it in a longer term so that we can visualize it afterwards. And this can be any web map service. So you might ask, what's under the hood then? We have an infrastructure as a service coming from European Weather Cloud. It's based on OpenStack, and this is for POC reasons. So this is a pathfinder, as we call it in EUMETSAT, to identify the benefits and how we can do this in a production afterwards. So you can see the specs are not that big. We have in CPU and RAM and block storage, we can also have a little bit more room for that, but we are especially limited on the GPUs. We have two physical A6000 GPUs presented as vGPU flavors, and we are using Kubernetes Archie as the flavor rancher to manage and provision these Kubernetes clusters. We are using OpenStack Cloud Control Manager, CSI plugins for read-write only access to the storage. We also have Longcon for read-write many, and we are using NVIDIA GPU operator to present these GPU resources to the pods. We are also having some instance groups to auto-scale the worker nodes, but as I said, the vGPU instance group is quite much tight in this case because we don't have many resources. Yes, you heard it right. We have A6000s, and this card is 5 years old, but our infrastructure is 5 years old as well. And this is a pathfinder, so we are still trying to figure out what we need in the next 5 years so that we can build our platform accordingly. These cards are presented as I said, virtual GPUs, and we have like a couple of flavors there presenting how much memory that we have on the vGPU side. And I must say that these resources are really scarce, so we need to be extra careful on how we spend that. As I also pointed out in the previous slide, we are using NVIDIA GPU operator to present all this because it simplifies the installation and maintenance and the operations, and it also bundles up a lot of nice tools from NVIDIA, and you don't need to, of course you need to configure them in the installation phase, but at least you have one source of ground truth that you can configure everything in one place. And we are implementing time slicing for better resource sharing and utilization. You might ask, time slicing, why not X? X can be in here MPS or MIC. I have a short answer for you, because we have to. Our card doesn't support anything else, so we have to use time slicing, and this is our only option to have vGPU sharing, to share some resources. But don't worry, I also have a long answer. So we are using GPUs mostly with SEM to segment images. And users are running repetitive, mostly unrelated data processing jobs. This is not a parallel processing in sense of MPI. So using something like MPS might be an overkill. Most of the time, we have some kind of a processor that is expecting an input data, and it's generating some kind of an output data. And if we lose the data in somewhere, we can always reprocess it and get the same data out of it anyway. So this is a nice trade-off in terms of memory isolation as well, because we can regenerate that output data anyway. And but this doesn't mean that we are not setting some ground rules. We do have some resource quotas, and we are watching the GPU utilizations anyway, but I think this is a nice trade-off with the limited GPU resources available. And we are also, in the future at least, we are also considering implementing retraining of the SEM2 using annotated data, and that might change the things a little bit. But for now, I think this is a nice trade-off. So I also would like to highlight a couple of challenges that we identified during our platform journey. One was to hiding infrastructure complexity from EO scientists. So these people are domain experts, and they are scientists, and they are really smart. But not everyone has to know how to present a vGPU to a pod or this or that. So this needs to be hidden from the Earth observation scientists, in my opinion at least. But a challenge rises again, how to integrate all these multiple tools, how to deploy and manage these tools at scale, and we also were missing a useful documentation. In that, we can actually contribute something back to the open source. And to do that, we came up with some design principles. First of all, use open source and open license of ecosystem. Second, we tried to automate everything with GitOps and infrastructure as code. We also adopted a Kubernetes first approach, where we were using official operators as a first choice. And if it is not mature enough or doesn't exist, we were using well-supported Helm charts. And if nothing is available and we have to build our custom solution, that is the only time that we are building our custom solution. And this is what we end up. Like these are the tools that I was mentioning in my previous slides as well, but let me just also give you a higher overview. We try to build a flexible and open and machine learning friendly platform for Earth observation scientists, and to make it a little bit easier for them in the beginning, we prepare the data for the end users, at least some of the data that are in high demand, but they can still bring their own data if they like. The scientists are already familiar with Jupyter Hub, and they were using it quite extensively. So we provided a hosted hub where they can interact with the other tools that we are providing in the platform, and also have some kind of a GPU processing capabilities to help them getting started. And of course, they don't have to use this hosted Jupyter Hub. They can bring their own tools, their own editor instead of a Jupyter Hub, or they can bring their own Geo server to visualize the features that we identified in the features database. But the gist of this slide is that we are maintaining some of applications that they are already using separately, so that we can have a collaborative environment for them. And I would like to have a few words on GitOps. Here, in the previous slide, I said one platform, many applications, one Git. But it is like also one Argo CD to rule them all as well. So we have all these different applications. We have Jupyter Hub, we have Label Studio, we have Nucleo, we have functions running on Nucleo. I will come to that. We have a cloud-native PG and PostGIS extension. And all these applications needs to be managed and not installed, first of all, and then managed, and then maybe day 2 operations to back the database up, etc. So if there is an operator in place, we can automate in coordination with GitOps best practices. We can automate all these different tools in at least one single ground truth, and it gives us consistency on how we present this platform to the end user. And this is how it looks like in the end. I know Jupyter Hub can introduce a little bit of complexity, sometimes, but providing a hosted hub gives us an opportunity to have some plugins already in place for them, such as the Jupyter GIS or Jupyter Lab Git. So these are the things that they don't need to worry about anymore. And we also have installed some of the tools and libraries that they would like to have in the end, so they don't need to run manual commands on a terminal or something like that. And for the labeling part, we are using Label Studio. I must say we did a huge trade-off between different tools like CVAT, DS Annotate. There are many tools when it comes to the image labeling, but we found Label Studio is the most extendable with the API and UI, so it was a nice gist, nice tool that we can move forward with it, and it's quite customizable. We are also using Nucleo as a service framework. There are many, but this serves the best for the Earth observation use case with the lower maintenance overhead. So Nucleo treats the code as a whole, and it can build a container image on the runtime, and then you just need to run this as a function. This was actually called processor in the earlier versions, and it fits our purpose really well, because most of the time what we have in Earth observation science is also processors that are deployed one another. So it is not a parallel as I described, but concurrent processes, and Nucleo handles this use case really well. And most of the climate scientists are very familiar with Python, and Nucleo is very Python friendly. It can integrate with Kubeflow pipelines or any other pipeline orchestrator as well, but the only downside of it, let's say, it lacks this kind of a built-in workload pipelines like Kubeflow pipelines or Argo CD workflows. So if you want to do end-to-end automation, the Earth observation scientist or the user needs to bring that logic into Jupyter Hub or into their code. Also, the function versioning is not the same as managing a model registry, but managing a model registry is also an additional overhead. And right now, we only have a couple of functions, so we can bundle everything up in an image and use that instead. And debugging the deployed functions can be tricky, and the images tend to be a little bit large. So, for example, the thing that I am doing right now is to build them outside of Nucleo and put it in some kind of a central registry so that I can just download it instead of building it on the runtime, because these Python libraries can be big, and you are also putting the model and the checkpoints inside of it. And the other difficulty was to integration with the Label Studio machine learning backend, because it was expecting a Docker Compose setup. So we did something manual there. We had to. And documentation can be a little bit tricky as well. And this is the ugly. This is the machine learning backend that I developed personally. You can scan the QR code and judge my code. As I said, the Label Studio was expecting a Docker Compose setup where it has a web application server, supervisor D, and RQ to schedule the training jobs, etc. So I thought, okay, I can replace all that with the tools that are already available on Nucleo, and then I can use the Label Studio's machine learning SDK to build the model and present it in a way that Label Studio expects. Fortunately, Label Studio is not that selective on how you can present this kind of an information. It just expects you to have some kind of a JSON. So that is very fortunate, in my opinion, because then you can actually replace the Label Studio with something else, because at the end of the day, the prediction and how this has been presented to the end user is just a JSON file. The rest can stay the same, obviously. And this is how it looks like, the Label Studio at least. I was planning to do this on live, but yeah, video is safer. So this is how it looks like. How many images? 1,800, something like that. This is already uploaded from an S3 bucket. You see here, I have the Dvorak labels that are coming from IB-Track database. And I also have additional labels down below called SAM. This will be using the machine learning model to annotate. And if you go to the model is already integrated with the system. I must say, all of this can be done from an API as well. And I also have a separate video to how to do that, but I think this is an overkill, so showing the UI is good enough. And once you set all these things up, you have all these images that you can export in the system. And here you see all these different labelings coming from the IB track database. And these are different types of storms, different categories. And in here, I would like to have my own. So let me just speed this up a little bit. Oops. So let's go. And here, if you go, for example, on the right-hand side, I have the SAM labels, and I have the auto annotation is enabled so that I can auto-detect the features. And then what I need to do is to select the label that I would like to give it. It was a Dvorak 3, I think. So I put the key point, and then SAM did the segmentation and generate the label. And you can see it's very well compatible with the data coming from IB tracks. And then you can accept the labeling, and then this label will be available to extract. And then you can extract all that information to the Earth System Feature Database. And you see on the left-hand side how we can deploy this with Cloud Native PG, but on the right-hand side, you see a visualization of the atmospheric motion vectors, AMVs for short, the movement of individual cloud or water vapor patterns in successive satellite images. You see in the previous demo, we had like multiple images of the same system. It was not the same. It was actually moving slightly. So when you export all that labeling into a database and try to visualize it again, you will see all these shades coming through Earth, visualizing the movement of that cloud or water vapor. What next? Well, we need to work together with EUMETSAT member states to develop tools for data preparation. We also need to run joint labeled campaigns to label more and more data. And we also need to identify the best available methods for each feature. And okay, of course, we need to make more data available for the experts so that they can do more on the model development. And I really like to train the ML models with, or the Nucleo SAM2 integration, I mean, with the labeled data. And I really would like to have better GPUs, to be honest. And we are also planning to improve and extend the Earth System Feature Database with more features and capabilities. And thank you very much. And if you have any questions, I will be pleased to answer them.
Hi.
Hi.
Just a single question. How large is your ML ops team?
Not that big. Like 1, 2, 3, 4.
Okay. And it works, or is it too much work?
It works with a caveat, with an asterisk. Of course, I would like to have a bigger team.
Okay, thank you.
Anyone else? Then, thank you very much.